Two objects, maybe light years apart, instantly influencing each other. No wires, no signals, just some kind of connection. It
Yeah.
sounds like pure sci-fi.
It really does, doesn't it? But that phenomenon, we call it quantum entanglement. It's actually a cornerstone of quantum mechanics. And today, that's what we're going to dive into.
Exactly. So our mission for this deep dive is to explore this really fascinating kind of counterintuitive analogy between quantum entanglement and something much more familiar, chemical bonds breaking apart.
Yeah, at first glance, they seem worlds apart, but there's actually a surprisingly similar story going on, at least at the beginning.
Okay, so in both cases, you've got some kind of parent system that splits up.
Precisely. Whether it's a tiny particle or a whole molecule, it splits, and the bits that come out, the descendants, well, their properties are linked.
Mhm.
Linked because they came from the same place and because of these really fundamental rules, conservation laws.
So it's not just a shared history. These conservation laws actually force a connection between the pieces. What kind of laws are we talking about, and why are they so, non-negotiable?
We're talking about things like conserving energy, momentum, angular momentum, the universe's basic accounting rules. They don't get broken. So when the parent splits, the total amount of these things has to stay the same. It just gets shared among the new parts.
Got it.
And that shared need to conserve stuff, that's really the starting point for our analogy.
And here's where it gets really interesting, apparently. While the analogy kicks off really strong, its real value, the thing that teaches us the most, is actually where it just completely falls apart. It's those points of breakdown that really show us how revolutionary quantum mechanics is. We're talking indeterminacy, superposition, and that famous spooky action at a distance Einstein mentioned, non-locality.
Exactly. Think of the analogy like scaffolding. It helps you get started, lets you build up some understanding, but eventually you have to kick it away to really see the unique and frankly astonishing structure of quantum reality itself.
Okay, that's quite a twist. The analogy works best when it fails. So how are we going to unpack this for you? Well, first, we'll tackle the weird world of quantum entanglement itself.
Then we'll look at the more familiar ground of chemical bond cleavage.
Right. Then put them side by side, see where they match up, see where they really, really don't.
And finally, what does it all mean, for future tech and our understanding of things?
Let's deep dive into it.
Okay.
So jumping right into the quantum realm. This is where our everyday intuition really takes a beating. Let's start with what makes quantum states so. Quantum, indeterminacy, and superposition.
Right.
It's not like flipping a coin where, okay, the result is hidden until it lands, but it was going to be heads or tails. In the quantum world, something like an electron spin, it isn't just unknown before you measure it, it's genuinely undecided.
Exactly. The electron isn't secretly pointing up or down. Before you measure it, it exists in what we call a superposition. It's like in all its possible states at the same time.
Like the coin literally being both heads and tails simultaneously.
Kind of, yeah. And it's the measurement, the landing of the coin that forces it to pick one, forces a definite result.
So just by looking, by measuring, you actually change the reality of what's there. And it's not even certain what you'll get, just probabilities.
You've got it. Measurement isn't passive watching in quantum mechanics. It actively changes the system. It collapses the wave function, that's the math describing all the possibilities, collapses it from that fuzzy superposition into one specific state.
Wow.
And yeah, the outcome is fundamentally probabilistic. Quantum mechanics can tell you the odds, very precisely, but not which outcome you'll get for sure in any single measurement.
Okay, I can see why that was unsettling for early physicists, especially Einstein. He, Podolsky, and Rosen wrote that famous EPR paper in 1935, basically arguing quantum mechanics must be incomplete.
Yeah, their argument, from a classical viewpoint, made a lot of sense. They said, look, if you can predict something about a particle over here by measuring its partner way over there without disturbing the first particle, then that property must have been real all along.
Like it had a definite value even before measuring.
Exactly. They called them elements of reality. We often talk about them now as local hidden variables. It's that gut feeling. Things have definite properties whether we're looking or not.
Which makes perfect sense for, say, chemistry, right? If I have a pair of gloves, I pull out the left one, I instantly know the other is right. It was right before I looked. But you're saying that intuition, while fine for chemistry, just doesn't hold up in the quantum world.
That's the crucial point, yeah. Now, onto these entangled systems. Entanglement happens when particles are created together in a way that links their quantum states. They become a single system.
A single system even if they fly apart.
Even if they fly apart. Their individual states are completely uncertain, maximally uncertain, actually. But the state of the whole system, the combined state, is known for sure. They share one single wave function.
So even across a galaxy, there's still one quantum thing. And that's the spooky action at a distance. You measure one, the other instantly knows.
It does sound spooky. But, and this is really important, it doesn't let you send messages faster than light.
Oh, okay. How come?
Well, imagine you're measuring one particle. You just get a random result, say, spin up or spin down. Your friend measuring the other particle, light years away, they also just get a random result.
Right.
It's only when you two talk later, by phone or email, limited by light speed, and compare your random results, then you see the perfect correlation. Oh, every time you got spin up, I got spin down.
Ah, okay. So the correlation is real and instantaneous, but you can't use it to send a deliberate message instantly. It creates correlation, not communication.
Exactly. Entanglement creates correlation, not superluminal communication.
So how do we even create these entangled pairs? You said it often involves a splitting. That sounds like our analogy starting point.
It is. A good example is particle decay. Imagine a neutral pion, which has 0 total spin. It decays into an electron and a positron.
Okay, 0 spin to start with.
Right. And the law of conservation of angular momentum kicks in. The total spin must remain 0. Now, the electron and positron are both spin 12 particles. They can be spin up or spin down, but individually, they're in a superposition.
So neither is definitely up or down until you look.
Correct. But because the total must be 0, if you measure the electron and find its spin up,
then the positron, no matter where it is, has to be found spin down if measured the same way, instantly.
Precisely. They're perfectly anti-correlated. It's called a spin singlet state. It's a superposition, really. Electron, a positron down, OR, electron down, positron up. You just don't know which until you measure one.
Okay, that's one way. What else?
Another very common way, especially in labs, is called Spontaneous Parametric Down-Conversion, or SPDC. You shoot a high-energy photon, the pump photon, into a special crystal.
And it splits.
It splits into 2 lower-energy photons called the signal and idler photons. And again, conservation laws are key. Energy and momentum are conserved strictly.
So the 2 new photons perfectly share the energy and momentum of the original one.
Exactly. And their properties, like polarization, can become entangled. For example, depending on the crystal setup, if you measure one photon and find its polarization is horizontal, you instantly know its partner's polarization must be vertical.
Again, perfectly correlated, no matter the distance.
What ties these methods together is that entanglement isn't some extra mysterious force field connecting them. It pops out directly from fundamental conservation laws meeting quantum indeterminacy.
So the universe needs to keep its books balanced, like total spin must be 0. But the individual particles don't have definite values until measured. So the only way to satisfy both rules is to link their potential outcomes, to make them correlated.
You've nailed it. Entanglement is nature's way of balancing the books in a world where individual accounts are fundamentally fuzzy until you look. It's a cosmic accounting trick.
Huh. A cosmic accountant. I like that. Okay, let's shift gears now to the chemical side of the analogy. Breaking bonds. A covalent bond, that's shared electrons between atoms, right?
Typically, yes. And in most stable molecules, those 2 electrons in the bond are spin paired. One spin up, one spin down. Chemists call it a singlet state. Their spins cancel out, giving a total spin of 0.
So just like our spin 0 quantum particle. That's a pretty strong starting point for the analogy.
It really is. Now, one way that bond can break is called homolytic cleavage, or homolysis. Think homo meaning same, olytic meaning splitting. It's an even split.
Even split.
Each atom involved in the bond gets one of the shared electrons. In diagrams, chemists use these little single-barbed fishhook arrows to show one electron moving.
Okay, 1 electron each. What do you get?
You get radicals. These are neutral species, but they have one unpaired electron. That makes them usually very reactive. They really want to find another electron to pair up with.
And this doesn't just happen, it needs energy.
Right. It's endothermic. You need to put energy in, like heat that's pyrolysis or UV light photolysis, to break the bond. A classic example is chlorine gas, ClElO, splitting into 2 chlorine radicals, Cla, when hit with UV light.
Okay, so that's the even split homolysis. What's the other way?
That's heterolytic cleavage or heterolysis. Hetero meaning different. This is an uneven split.
Uneven, so one atom gets greedy.
Pretty much. One atom takes both of the shared electrons from the bond. We show this with the standard double-barbed arrow, meaning a pair of electrons is moving.
And what does that leave you with? Not radicals this time.
Nope, you get ions. The atom that took both electrons becomes negatively charged an anion. The atom left behind becomes positively charged a cation.
Okay. And when does this happen?
It's more likely with polar bonds, where the electrons weren't shared equally to begin with, and polar solvents can help stabilize the ions formed. Think of, say, a carbon-bromine bond. Bromine is more electronegative, more electron-hungry. It might just take both electrons, leaving a positive carbon bit and a negative bromide ion.
Okay, homolysis gives radicals, heterolysis gives ions. But here's the key difference you mentioned earlier.
Yes, the crucial distinction. In both chemical cases, the products, the radicals, or the ions, they have definite, knowable properties right from the moment they're formed.
Like a chlorine radical is a chlorine radical with a specific structure, a specific spin state, even if we haven't measured it yet. No fuzziness.
No fuzziness, no superposition of states, no fundamental indeterminacy. Chemical diagrams show electrons moving deterministically from one well-defined state to two other well-defined independent states.
Independent. That sounds important too.
Very. It's a clean break into separate things. That's a huge contrast to the quantum case, where the pieces remain fundamentally linked and individually undefined until measurement.
All right, time for the main event, putting these side by side. Where does the analogy actually hold water, and where does it, completely spring leaks and reveal the quantum weirdness?
Well, the strongest part, the foundation, is definitely those conservation laws. They govern the splitting in both worlds.
Especially the conservation of spin, right? You said that was almost identical.
It really is the most striking parallel. In chemistry, you start with that spin-paired covalent bond, total spin 0, a singlet state. Homolysis breaks it, giving two radicals, each with one electron, spin 12.
And to keep the total spin 0.
The two radicals must have opposite spins, one up, one down. They are created anti-correlated.
Okay.
That is conceptually and even mathematically identical to our quantum example of a spin 0 particle decaying into an entangled pair of spin 12 particles. Total spin must be conserved, so the components must have opposite spins. That's the bedrock.
And you mentioned energy and momentum conservation applies in both, too, like needing energy to break a bond and the SPDC photons sharing the original photon's energy.
Yep. Those universal laws hold firm across both domains. The universe balances its books, whether it's chemistry or quantum physics. That part of the analogy is solid.
But, and it's a big but, this is where things diverge dramatically.
Oh, yeah. Big time. The divergences aren't just small details, they're fundamental differences in the nature of reality as described by chemistry versus quantum mechanics.
And the biggest one seems to be about reality itself, that whole hidden variables thing. Chemistry seems to agree with our intuition, right?
Completely. Chemical radicals are ions. They have definite properties the instant they're made. A chlorine radical has a specific spin direction, even if you don't know it yet. It's like the gloves finding the left glove reveals the other was already right. It doesn't cause it to become right. That's classical local realism.
But quantum mechanics says no.
Quantum mechanics says entangled particles do not have definite properties before measurement. They're in that superposition. And here's the absolute killer point. The correlations we see cannot be explained by any local hidden variable theory. That was John Bell's huge contribution.
John Bell. He figured out a way to test this, to actually ask experimentally if reality is predetermined or genuinely fuzzy.
Essentially, yes. In 1964, he came up with Bell's theorem. It showed that if local hidden variables were real, then the correlations between measurements on entangled particles could only be so strong. There'd be a limit, defined by what we call Bell's inequalities.
Okay, a limit based on classical assumptions.
But if quantum mechanics was correct, with its weird non-local correlations, those limits would be exceeded. The correlations would be stronger than any classical explanation could allow.
So he turned a philosophical debate into a testable prediction. Did we do the tests?
We certainly did. Starting in the 70s and getting incredibly precise with loophole-free experiments around 2015, the results are in, and they are crystal clear.
Okay.
Bell's inequalities are violated consistently, exactly as quantum mechanics predicts. It's a fatal blow to local hidden variables. The spooky correlations are real, intrinsic, and non-local. Reality is that weird.
Wow. Okay, so that just fundamentally breaks the chemical analogy. Our intuition is wrong at that level. What's the next big difference?
It's about the connection itself, locality, and separability. In chemistry, you break a bond, you get two separate things. Radicals, ions, they become independent local entities.
Their connection is just a memory of the past, like We used to be bonded.
Exactly. It's a historical correlation, not an active ongoing link.
But entangled particles.
They remain one single, indivisible, non-local system. Regardless of distance, measuring one instantaneously affects the state description of the entire system, including the distant partner.
So they aren't really two things connected, but more like one thing spread out.
That's a great way to put it. They can't be fully described independently. There's just no equivalent to that holistic, non-local connection in chemistry.
Okay, and one more difference. The nature of the bond itself.
Right. A chemical bond.
Well, it's a physical thing.
Right.
You can talk about electron orbital overlap, electrostatic forces. It's localized in space, has a certain strength you can measure.
And tangible, yeah. Quantum entanglement. It's not a physical string or force. It's purely a quantum mechanical correlation. An abstract mathematical property describing statistical links between potential measurement outcomes.
So let's try to sum that up. Chemistry. Definite properties, independent local products, physical bond. Quantum.
Yeah.
Indeterminate properties, single non-local system, abstract correlation. Is that about right?
That's a perfect snapshot of the key contrasts.
So after pulling it all apart, what's the real lesson here? What's the value of an analogy that, well, breaks down so spectacularly?
The value is precisely in the breakdown. Okay, first, pedagogically, it's useful. It gives us a starting point. The idea of splitting while conserving something, like spin, that resonates with chemical intuition. It's an accessible entry point.
A way in.
A way in. But the real learning happens when you see where it fails, when you're forced to confront the fact that quantum reality isn't just a slightly modified version of classical reality. It's fundamentally different.
So abandoning the analogy forces you to grapple with the actual weirdness, the indeterminacy, the non-locality.
Exactly. It's like that scaffolding we talked about. You use it to get up, but then you have to kick it away to see the building properly. The analogy's failure illuminates the true revolutionary nature of quantum mechanics. It forces the aha moment, or maybe the wait what moment.
That's a powerful idea. And it leads to another big difference, right? What you do with the products.
Absolutely. Think about chemical radicals from hemolysis. They're usually super reactive, unstable things, short-lived intermediates. They're not the end goal, they're just a step on the way to something else. The system wants to get rid of that unpaired electron, move away from that correlated state.
Okay. But entangled particles.
Totally different story. An entangled pair isn't an unstable intermediate you want to get rid of. It's a resource. A stable, potentially long-lasting resource that you want to create, protect from noise, and use.
Use the correlation.
Yes, exploit that non-local correlation. It's not a bug, it's a feature. A very powerful feature.
And that's where all the futuristic-sounding quantum technologies come in.
That's exactly it. Entanglement is the engine behind so much of it. Quantum computing, for instance. Entangling quantum bits, or qubits, lets you create these massive computational spaces that grow exponentially.
Which allow for those super fast algorithms, like Shor's for breaking encryption.
Shor's for factoring, Grover's for searching, yeah. Exponential speedups for certain problems. And entanglement is also key for quantum error correction, making these delicate quantum computers more robust.
Okay, what else? Quantum cryptography.
Right. You can use entangled particles shared between two parties, let's call them Alice and Bob, to create secret keys for encryption. The cool part is, the laws of quantum mechanics guarantee that if anyone, an eavesdropper, Eve, tries to listen in by measuring the particles,
it disturbs the entanglement.
It has to. Measurement changes the state. That disturbance creates errors that Alice and Bob can detect immediately. They know their channel isn't secure. It offers provable security based on fundamental physics.
That's amazing. And quantum teleportation, is that like Star Trek?
Not quite beaming people around, unfortunately, but it uses entanglement as a resource to transmit the quantum state of a particle from one place to another without physically sending the particle itself.
So you're sending the information, the blueprint, using entanglement as the channel.
Sort of, yeah. It's a crucial building block for future quantum networks, maybe even a quantum internet someday.
So, wrapping this all up, this quantum strangeness, this spooky action, it's not a mistake or something we need to explain away with simpler analogies.
Not at all. It's a fundamental truth about how the universe works at its deepest level. It's a completely different paradigm from our classical intuition, stranger than we probably imagine.
And we're just starting to figure out how to use it.
We really are just scratching the surface of what's possible by harnessing these non-local connections.
So here's a thought to leave you with. As we keep building technologies based on this genuinely spooky connection, what other deep fundamental differences might still be waiting for us to discover? differences between the world our intuition tells us exists and the weirder quantum reality that actually runs the show.